Hello and welcome. We will continue with our course on energy conservation and waste heat recovery. So, in the last lecture what we did was we kind of wrapped up our discussion on energy storage systems. During the course of that series of lectures, we learnt about several energy storage technologies, some of them mechanical storage. We talked about superconducting magnetic energy storage, then we talked about electrochemical storage, chemical storage, thermochemical storage and so on, and thermal energy storage of course. So, what I will do is, in this lecture we will just spend some time to solve a few problems based on what we have learnt, and in the process what we are going to do is we are going to put into use our learnings to see that in practical situations, if we have an energy storage system, how do we calculate let us say the power that we can get out of it, the efficiency of that energy storage system and so on. Okay. So, the first problem that I have is from compressed air energy storage. So, what it says is, consider a compressed air energy storage facility, and what we have to do is we have to calculate airflow rate, we have to calculate compressed air temperature and storage volume. Okay. And several things are given. For example, what is given is the peaking unit is 1500 megawatt hour, all right, and it is charging for 7.5 hours, and then the compressor inlet conditions are given, pressure and temperature, and compressor exit pressure is also given. The peaking turbine efficiencies and the compressor efficiency both are given, and they are not very high as we can see, okay, and then a few properties are given. So, if we are given this problem, how do we solve? Okay. So, let us remember what did we do. Let us write down what all is given to us. Okay. What is given to us? So, the problem is on compressed air energy storage. Given is compressor inlet. What is that? It is 20 degrees centigrade and it is 1 bar, okay. So, or 1 atmosphere. Compressor outlet, the temperature is not known, what is known is it is at 100 bar, okay. So, this is temperature, this is pressure, all right. What else is given? It is given that the storage or whatever, the energy storage or energy delivered should be equal to, at turbine should be equal to 1500 megawatt hour, clear. And then there are a few other things that are given, like the compressor. Okay, so the compressor efficiency is 70% and the turbine efficiency, the peaking turbine that is 60%, and a few other properties are given. Oh, it is also given that the charging time, so which is the time when the storage happens, is 7.5 hours. So, with these conditions, what do we have to do? What we have to do is we have to solve this problem. Okay. So, let us, what we will do is, instead of going into the details of calculations etc., we are going to focus more on the steps. How do we systematically solve a problem like this? Okay. So, this is compressed air energy storage, and the first thing that is given is a compressor. Okay. What is happening in the compressor? Now, recall what happens in the compressor. Let us say this is my TS diagram, and it is more of the compressor stage in a Brayton cycle, or it is similar to the compression stage in the Brayton cycle, where this is my P1 or P inlet, this is my P outlet. Okay. Again, recall, if I just simply draw a compressed air energy storage. This is my compressor, this is my ground level, and this is my storage reservoir, and then again this is my peaking turbine, and from here I get electricity and I get this exhaust, and there is probably a heat exchanger over here. Clear? So, what I have is I have the point here, compressor inlet and compressor outlet. So, this is Pi and P naught. What happens over here is, if I look at the cycle, then this is my point I, or let us call it 1, and let us call this 2. So, this is my 1 to 2, and if it were isentropic, then I would have landed up at 2s, but since the compressor is not isentropic, I will end up somewhere in 2. Okay. This pressure is what? This pressure is 1 bar, and this pressure is 100 bar. All right. So, my first step is, let me try to put it half and half here and keep solving. So, my first thing is I am going to use the relation using, if it is isentropic compression, I can write T2s by T1 is going to be P1 over P2, okay, to the power gamma minus 1 by gamma. Okay. P1 equals to Pi is equal to 1 bar, P2 is equal to P outlet is equal to 100 bar. So, therefore, this gives, I will quickly just go through 273 plus 20, remember these are absolute temperatures, times 100 over 1, and for air, gamma for air we know is 1.4. Otherwise, from the given data we can also calculate, we have the value of R and the value of Cp for air given. So, we can also calculate gamma, but we know that gamma for air will come to be 1.4. So, let us write that 1.4, a 0.4 over 1.4. So, this gives me T2s is 1092.2 Kelvin. Okay. Next what we will do is, but this is this temperature, I need the outlet temperature of the compressor. So, use the definition of efficiency. Okay. So, I can write T2s minus T1 divided by T2 minus T1 is equal to the compressor efficiency, which is given as 0.7. So, from here using everything I will get T2 is going to be 1434.7 Kelvin. Okay. So, this is one data point I have. All right. So, if you look at the question once again, what I have got is the second answer, compressed air temperature, and this is my compressed air temperature, right. So, let us write that down. This is my compressed air temperature. So, this is one answer. Now, I have to calculate two more things, and those are what is the air flow rate and what is the storage volume that would be required. So, how do I calculate that? Okay. I have the temperature value right now. Okay. So, what we will do is next is for a turbine input, for a turbine output, what is it given? It is given that the turbine output in this case, and when I say turbine, it is the peaking turbine, is 1500 megawatt hour. Right. I also know that the turbine efficiency is given to be 0.6. So, therefore, turbine input power is going to be 1500 divided by 0.6 megawatt hour or 2500 megawatt hour, right. This is an important piece of data. Now, what is this 2500 megawatt hour? So, therefore, if I look at it, this is the energy that is being delivered from here. So, that must be equal, assuming there is no loss, that must be equal to the energy that I pumped in, right, assuming no loss in the heat exchanger, no loss through the reservoir. Okay. Since it is not given, those are assumptions we are going to make. Clear? So, therefore, I can write from here then that for the compressor, that is by compressing the air, that is the energy I have stored. So, therefore, I can write m dot air, which is the mass flow rate of air, or okay, times Cp, right, times T2 minus T1, sorry, this is the mass of air, not mass flow rate, I am sorry, Ma will be equal to 2500 megawatt hour, where m dot A is mass of air compressed. Clear? So, if that is the case, I will get, okay, megawatt hour you have to change. So, 2500 times 10 to the power 6 and hours you have to put it as 3600. Cp is given to us, Cp is 1.05 kilojoules per kg Kelvin, that value is given in the, I am sorry, that value is given over here in the problem. So, therefore, and T2 and T1 we already know, we have calculated T2 and T1 was given to be 20 degrees or 293 Kelvin. Therefore, this will give me m dot air is equal to 7.5 times 10 to the power 6 kg. Okay. So, next what we will do is, assuming air is stored at 100 bar and 20 degrees centigrade. Recall here, after this it is at 100 bar and it is cooled down by this heat exchanger, and we are assuming that it will be cooled down to the original temperature of 20 degrees centigrade. It may not be, but that is the assumption we are making, okay, because the problem statement says make and state necessary assumptions, all right, make and state necessary assumptions, all right. So, therefore, 100 degrees and 20 100 bar and 20 degrees centigrade, I can write the total volume required for storage. So, therefore, storage volume, what are we going to use? We are going to use PV equals to MRT, air, okay, MRT by P, and in this case what is it? P is P2, MART. So, what did we have? 7.5 10 to the power 6 times R, it is given already 0.28475 kilojoules per kg, clear. So, what we will do is we will convert it to joules, therefore, 284.5 times the temperature is again back to T1, which is 293, divided by the pressure is 100 bar, 101 bar is 10 to the power 5 or 100 kilopascals or 10 to the power 5 pascals. So, this will be in meter cubed, turns out to be 62520. Okay. These calculations you may get a little different values, that is okay. So, therefore, I would write storage volume is this, and this is also an answer. And the last part is easy because they asked whatever the last part was, calculate air flow rate. So, air flow rate in compressor is going to be what? The volume divided by 7.5 hours is that is given. The charging time is 7.5 hours here. So, therefore, I will write it as 62519, that is the volume, divided by 7.5. So, that is going to be the meter cube per hour, okay, and whatever it comes out to be. All right. Okay. So, this is how we solve these problems. So, first thing that we did was we found out the temperature at 0.2 because that is the compressed air temperature. Next, we had to find out what is the volume that is required. So, for that we were given what is the output power. So, using turbine efficiency we got the input power to the turbine, which must be equal to the energy input or input energy to the turbine, and that must be equal to the input energy that was stored in the reservoir, okay, assuming no losses again. So, therefore, if we know the input energy, what we could find was that is equal to mCp delta T. Okay. So, m dot times Cp times T2 minus T1. So, from there we found out what is the mass flow or what is the mass of air that was stored. Okay. So, mass of air was known, and then knowing the assuming that the of course, the pressure will be at 100 bar, and assuming that the temperature it was cooled down by this regenerative heat exchanger back to 20 degrees, which is an assumption which we clearly stated. We could find out using the ideal gas law, we could find out what is the volume of the storage, and then once we know the volume, this is what was stored. It took 7.5 hours to fill up this by the compressor. So, divided by 7.5 will be the volume flow rate of air into the reservoir. Okay. All right. So, I hope this problem gave you a feel of how to solve these problems, right. So, this was a compressed air energy storage type of a facility, energy storage facility, and we given some input conditions and some assumptions, and making some assumptions we were able to get some values. Okay. Now, you may get a problem, you may have to solve a problem where some of the things that we solved for are given and some of the things that was given in the problem is unknown. So, it is more the method that we used which is important. Okay. Okay. Let us move on to the next problem, and this problem is on pumped hydro. Okay. So, the pumped hydro case, what is given is there is a pumped hydro storage system. The water capacity or the volume of water that is pumped up from the base reservoir to the top reservoir is given. So, remember you have a base reservoir here, and then at the top of the cliff you have another reservoir. So, this is my base reservoir and this is my top reservoir. Okay. So, this is my pumped hydro problem, and he said that it can be released for generating electricity over a 5-hour period. So, when we actually extract the energy out of when we use the stored energy, we can use it for 5 hours. If the effective head is 500 meters, so effective head is may or may not be equal to total head. Okay. This is my head, the effective head may be less than this because there will be some losses. Okay. Effective head is 500 meters and the generator efficiency is 90%. Calculate the average power output and the total electrical energy produced in 5 hours. So, this is what is shown here in this here again. So, if the effective head is 500 meters, generator efficiency is given, calculate the average power output and the total electrical energy produced in 5 hours. All right. So, let us first do this and then we will come to the second part. So, first we will say the capacity, okay, this is the pumped hydro problem. Okay. What is given? We know the capacity is 7 times 10 to the power 6 meter cubed. This is the volume of water that is pumped up. Clear? So, therefore, generating flow rate, this is when the power is generated, what is the flow rate into the turbine, right? What is the flow rate into the turbine during power generation? So, I can write it as 7 into 10 to the power 6 divided by, so this is the amount, the volume which is fed to the turbine over a period of 5 hours. So, I would write it as 5 into 3600, that is the number of seconds in 5 hours, meter cube per second, and it comes out to be 389 meter cubed per second. Okay. So, what have we asked for? We are asked what is the average power output. So, average power output, what is that going to be? Okay. So, power is, we know, volume flow rate times pressure drop, right. So, we can write it as rho g h t, which is the, what is it? This is the effective head in the turbine, times flow rate, or okay, let me write down here, flow rate normally we denote by V, okay. So, you would also write it as Vt, V turbine, okay. And then what? This is 1, this is the flow rate, times the output is, this is the input to the turbine, output would be, we have to multiply that by the turbine efficiency, which is, sorry, the generator efficiency, okay. Sorry, I will write it as eta g, the generator efficiency is given as 90%, clear. So, therefore, this turns out to be, everything is known, rho is like 1000, I will write it for the first time, next time I will not, 9.81 times pumping head was 500 times the volume flow rate is 389 times the generator efficiency is 0.9, and this will be, what is this is going to be watts, clear, and this turns out to be 1.72 gigawatts. Okay. So, this is my first answer, and what is the energy produced? That is easy, because this is the energy that is produced times over a period of 5 hours. So, I would write it as 1.72 times 5 gigawatt hour, and this is 8.6 gigawatt hour. Clear? All right. So, this is how we have solved it. What is the next problem? The next part says that it takes 6.5 hours to refill the reservoir, which means during the pumping time. So, because of frictional drag, the effective head when pumping is 530 meters, and for pumps having an energy efficiency of 90%, calculate input power to pumps, total electrical energy, the same thing like in turbine, we want to do it for the pumps and overall energy efficiency of the pump storage plant. Okay. So, for pumping, second part, so here I will move a little fast now that we know how to do things. So, effective head HP is 530 meters, okay. And what is the flow rate? So, this happens over 6.5 hours. So, what we will do is we will again see the same volume flow rate, 7 into 10 to the power 6 divided by 6.5 into 3600, and that turns out to be 299 meter cube per second, okay. So, therefore, input power is going to be rho G pumping head times the flow rate through the pump. This one this time is divided by the pumping power, because the input power to the pump has to be more than the energy that is gained by the water that is pumped up. Okay. So, this we know all the values here. So, I am not writing everything, and this turns out to be 1.75 gigawatts. Okay. So, this is my A. Second one is electrical energy for pumping, that is 1.75 times 6.5 gigawatt hour, and that turns out to be 11.2 gigawatt hour. C. Last one was, what is the overall efficiency of the pumped hydro storage plant? Okay. So, this one, be very careful. This is going to be energy output divided by energy used. Okay. I will write down again in capitals, not power. Normally, regularly when we solve for thermodynamic cycles, etc., we use power input versus power output versus power input. So, watts, but here we have to use energy. Why? Because the input and output do not happen simultaneously. In a cycle, it happens simultaneously. So, the time is the same, right. So, per unit time whatever is coming in, per unit time that is going out. So, we do not care about the, so the ratio of the power gives the efficiency. But in this case, it is a ratio of energies, right. So, therefore, we are not going to use the power values. Power values, if you recall, what did we get? We got 1.75 is the input power and 1.72 is the output power. So, efficiency is almost close to 100%, but that is not the case, right. So, therefore, here what we will do is, here we are going to use this one, we are going to use the power which is 8.6 over 11.2, and that turns out to be around 77%. Clear? All right. So, I think these two problems sort of give us a feel of how to solve these problems pertaining to energy storage plants. I hope that kind of wraps up our discussion. Okay, let me do one thing. I had one more problem, so I will leave it for you. This is for thermal energy storage, and what I will do is, I will just talk about a base load 1000 megawatt power plant. It is designed with a sensible energy storage system. So, we are talking about, so this one is about a pressurized water storage. Okay. The thermal energy stored is called to produce 4000 megawatt hour of electrical energy daily. So, output is 4000 megawatt hour daily, all right. And then we have accumulators, a series of accumulators. The accumulators are 4 meters in diameter each and are well insulated, so that the external heat transfer coefficient is given, the storage time is given, and the maximum and minimum pressures are also given. Okay. The outside temperature is given and all that stuff. So, what do we have to do? We have to calculate the turnaround efficiency. So, recall here what happens is, the water is compressed from 200 K to 2000 kilopascals, 200 kilopascals to 2000 kilopascals. So, there is an amount of energy stored, and we solve that, how to calculate that, remember, okay, rho f times HF2 minus HF1, okay, and the rho f typically we take the average specific volume, all right, over the two temperatures. Okay. And these are both saturated conditions, we will get the properties from steam tables. So, this part we did already, exactly taking the exact same values when we were discussing. Okay. Next, what happens? It is stored at 2000 kilopascals and corresponding saturated temperature, which turns out to be 212 degrees centigrade. But then what happens is, as it is stored, it loses heat, and because outside temperature is 25 degrees centigrade. Okay. And how long is it stored? It is stored for 15 hours. So, use the turnaround efficiency formula, where the time constant you have to first calculate, right, rho C V over H A. So, V and A very nicely for a cylindrical accumulator, the volume is pi d squared over 4 times the length, and the outer area is again pi d times the length. Okay. So, we have to use this formula, we will get the time constant, put it in that equation, and we are going to get the turnaround efficiency. And then what is the total amount that we require? 4000 megawatt hour of electrical energy daily. So, from there we use that formula. So, we figure out how much is the amount of how much is the accumulator volume that we need, and I mean using that we can find out what is the accumulator volume that we need. Okay. So, we will leave this maybe for an assignment or something, and we can use whatever we discussed to solve this problem. Okay. So, again thank you very much. That kinds of now truly wraps up our energy storage discussions, and in the next lecture we will take up a new topic. Thank you.